Okay, well, I want to take a look here at a couple more examples of trigonometric substitution. And so let's take a look at the integral I have right here. The integral of the square root of 9 minus x squared divided by x squared. So we're going to solve this using a trigonometric substitution. And referring back to the notes we did yesterday in class, it looks like we're probably going to want to use pattern number 1 on this one. Because notice here in the numerator we have a constant squared minus the variable squared, which fits pattern number 1 perfectly here. So let's let x equal 3 sine theta. So if we let x equal 3 sine theta, that means that the differential of x is going to be 3 cosine theta d theta. So let's go ahead and put those substitutions into our integral here. So we'll have square root of 9 minus x squared, which in this case would be 9 sine squared theta, all divided by x squared, which is still 9 sine squared theta. And then dx is 3 cosine theta d theta. So 3 cosine theta d theta. Okay. So let's see what we now have. This up here, of course, you can factor out a 9, and you'll be left with 9 times 1 minus sine squared theta. But what's 1 minus sine squared theta? It's cosine squared theta. So what we have here under the radical is actually this part right here. That's actually 9 cosine squared theta. 9 cosine squared theta. So if we take the square root of 9 cosine squared theta, that would be 3 cosine theta. So we now have integral of 3 cosine theta over 9 sine squared theta times 3 cosine theta d theta. And it looks like the constants all cancel out here. You got 3 times 3, which is 9, and we got a 9 on the bottom. So constants go away, and we end up with cosine squared theta over sine squared theta. So cosine squared theta over sine squared theta d theta. Now comes pretty much a point of decision, where you want to go from here. I can't get the derivative of the bottom on the top. So is there another way of writing cosine squared theta over sine squared theta? That could be written as cotangent squared theta. I'm going to start going left to right now. So does that help me any, rewriting this as cotangent squared theta? Well, at this point, not really. It's still not easy to integrate this. But there is a trig identity we can use here that will make this come out much nicer. Cotangent squared theta could be written as cosecant squared theta minus 1. So I'm going to rewrite this as integral of cosecant squared theta minus 1 d theta. This is a common identity for Math 142, pre-calculus 2. So let's now this is easy to integrate. The antiderivative of cosecant squared theta. What function has cosecant squared theta as its derivative? It's not one we've seen very often, but we did talk about it in Math 151. The derivative of cotangent is negative cosecant squared theta. So the antiderivative of cosecant squared theta would be negative cotangent theta minus, and the antiderivative of 1 with respect to theta will just be theta, and then plus c. So the integration's now done, but we now have to put it back in terms of the original variable x. We started in terms of x, so we have to end in terms of x. So to convert this back into terms of x, let's go back to our original substitution up here. We let x equal 3 sine theta. So that means sine theta has to equal x over 3. And if sine theta is equal to x over 3, let's draw a picture of that angle. So here's angle theta. Sine, of course, is opposite over hypotenuse. So let's let the opposite side be x and the hypotenuse be 3. So by the Pythagorean theorem, the missing side down here, the adjacent side, is going to be the square root of 9 minus x squared. Oh, it's out of the picture there. There we go. Now you can see my triangle. So let's go back to the answer that we got. Negative cotangent theta. So looking at our triangle up here, what is the cotangent of this angle theta? What would be the cotangent of theta? Well, cotangent, of course, is adjacent over opposite. So it'll be square root of 9 minus x squared over x. So negative square root of 9 minus x squared over x. Now what do we do with just this theta here? There's no trig function in front of it. So the triangle that we drew up here isn't going to help me figure that out. So for that we have to go back to the equation we got right here. Sine theta is equal to x over 3. Well, if sine theta is equal to x over 3, that means that theta is going to equal the inverse sine of x over 3. So we replace the theta in our answer here. We replace our theta with minus inverse sine of x over 3 plus c. And that's our solution. So what were the keys to evaluating this integral? Well, the first thing, of course, is we had to identify what substitution we're going to make. And then once we identify what the substitutions are going to be and put them all into the integral, it's mostly just a bunch of algebra to simplify it. But this was key right here. Rewriting the cosine squared over sine squared as cotangent squared, and then changing cotangent squared into cosecant squared theta minus 1. Because both of these terms were easy to integrate. Okay? So I have a second example I'd like to look at. And bear with me here, I'm trying to work this so I don't move the camera around too much. So I got the camera attached to one of those chemistry, one of those little chemistry stands. So we'll see how this works. Let's try this integral. The square root of 1 minus 4x squared dx. Now, what's different about this one, notice, is there's a 4 here in front of the x squared. It'd be nice if that was just x squared. So why don't we factor a 4 out of both terms here under the radical? So if we factor a 4 out, we'll have 1/4 minus x squared dx. Now, what can we do with that square root of 4? Well, square root of 4 is 2, and that's a constant, so we can move that 2 outside of the integral. And that'll leave us with the square root of 1/4 minus x squared dx. So it looks like we have a constant squared minus the variable squared. So it looks like the same pattern as last time. it still fits. It still fits this first pattern here: constant squared minus variable squared. In this case, though, a would be one half. So let's let x equal 1/2 sine theta. So we're going to let x equal 1/2 sine theta. Which means that the differential of x will be 1/2 cosine theta d theta. Okay, so putting those substitutions into our integral, we'll have 2 integral of square root 1/4 minus x squared, which in this case would be 1/4 sine squared theta, and then dx is 1/2 cosine theta d theta. Well, once again, the 1/2 here is a constant factor. We can move it outside of the integral, which basically just gets rid of the constants we've got so far. So let's now rewrite it like this. Times cosine theta d theta. So I move that 1/2 out of the integral, which cancels the 2. And we're now at this point here. Excuse me here. All right. What can we do here? Of course, we can factor the 1/4 out. Leaves me with 1 minus sine squared theta. Now, what's 1 minus sine squared theta? Everybody should know that. That's cosine squared theta. So what we have here is the square root of 1/4 cosine squared theta. And the square root of 1/4 cosine squared theta is 1/2 cosine theta times cosine theta. So it looks like we end up with 1/2 integral of cosine squared theta d theta. Well, this looks like one of those expressions we also talked about yesterday. We said yesterday that there is a nice identity for this if you need to integrate this by hand, and that was cosine squared theta is equal to 1/2 plus 1/2 cosine 2 theta. So let's put that substitution in for the cosine squared theta, or that identity I should say. 1/2 integral of 1/2 plus 1/2 cosine 2 theta d theta. Well, both of those terms are easy to integrate, or should be easy to integrate. So let's do that. We got the 1/2 out front, and let's take the antiderivative here of each term. The antiderivative of 1/2 with respect to theta is 1/2 theta. Now, the antiderivative of cosine 2 theta is 1/2 sine 2 theta plus c. Now, let's clean that up a little bit. Let's go ahead and multiply all the 1/2s and everything, and distribute the 1/2 here through the parentheses. So we'll have 1/4 theta plus, looks like we're going to have a 1/8 sine 2 theta. Plus c. Now we got to put everything back in terms of x. And this is where the work begins for us, really. Because what do we do with this sine 2 theta right here? That's a problem. But if we remember from Math 142, there's a nice identity for this, sine 2 theta. Sine 2 theta is equal to 2 cosine theta sine theta. That was what was called the double angle identity for sine. So rewrite the sine 2 theta here as 2 cosine theta sine theta. And I'm going to need to go to another sheet of paper here. So here's where we are so far. We got an answer of 1/4 theta plus 1/8 sine 2 theta plus c. And we're going to replace the sine 2 theta with 2 cosine theta sine theta. Sine theta cosine theta plus c. And let's now draw our triangle again like we did before, going back to the original thing we've got here. We let x equal 1/2 sine theta. So that means that sine theta is equal to 2x. Sine theta is equal to 2x. If sine theta is equal to 2x, that means the opposite side has to be 2x. The adjacent, or the hypotenuse has to be 1. Opposite over hypotenuse is sine. And by Pythagorean theorem, this side will be 1 minus 4x squared, square root the whole thing. Okay, square root of 1 minus 4x squared. So, let me get this picture in a proper location here where we can actually use it. Let's see. Not a lot of space here. How about if I do this? There we go. So, 1/4 theta. What's theta going to be? Well, if sine theta is equal to 2x, theta is going to be the inverse sine of 2x. So we'll have 1/4 inverse sine of 2x plus, well, 1/8 times 2, of course, is 1/4, times sine theta. Sine theta is 2x. Times cosine theta, which would be square root of 1 minus 4x squared over 1, or just square root of 1 minus 4x squared. And let's see, what's the remaining thing I can do with this, if anything? Well, we can make the 1/4 times 2 here. We can make that a 1/2. So I would say for the final answer, 1/4 inverse sine of 2x plus 1/2 x square root 1 minus 4x squared plus c. A lot of work, but I don't know about you, I love this stuff. I love drawing the triangles and finding the missing sides and making the substitutions. And for simplicity, I'll take the problems that I did here and scan them and post those on the Angel webpage for us. And that's all for today, and we'll see you tomorrow where we'll be working with integration by partial fractions. So see you tomorrow.